Okay, so um, last time we were introducing the problem of multiple comparison between that is the problem which arises when we do many tests. So let me recall what was the problem. So assume simply that we have I don't know n tests. So and each test has a significance level of alpha. So um, so each test has its own hypothesis, like H0 null hypothesis. Uh, so this is the null hypothesis for the first test. Then the second test has another null hypothesis. Um, and the problem is that the probability that I reject let me write it in this way. I reject H0, let's say 1. I reject one of the null hypotheses, one of the H0 ones. H0 is provided they are all true. So provided that H0 holds for every E. So so let me recall, a significance level of alpha means that the probability that I reject H0 in a particular test, say the test I, provided that H0 I holds, is equal to alpha, more or less, smaller or equal usually. But if we do many of these tests, this probability will be in general greater than alpha. The problem, the probability of making an error while doing many tests increases. So in general, this probability will be greater than alpha. And in some cases, we want this second quantity to be smaller than alpha. For instance, if we are checking, last time we were doing the example we have a class of students. We want to check, I don't know, we have 10 desks and we want to check whether they are copying or not. So we do a test on the exams that they gave us back, and we perform that test with a significance level of 0.05. There are 10 of them, and we don't want really to accuse one in a of doing something which he didn't do. So we want this second quantity, the probability that we make an error on the overall test, on the overall quantity of tests. We want that this quantity to be smaller than alpha. So, for instance, one solution is to perform the so-called Bonferroni correction of the significance level of the tests. So if there are n tests, we take a significance level for each single test of alpha divided by n. And with this choice, we are sure that this quantity here is smaller than alpha. And we did some computations. I mean, this can be easily shown, of course, provided that the tests are performed independently. I don't know, because if I do the same test n times, it will be with the same data, it will still be alpha divided by n. But if they are independent, these tests, and each one is with a significance level of alpha divided by n, I'm sure that the probability of making an error while of accusing somebody while they are not doing anything, it is smaller than alpha, and the computations are actually easy, so we can. Well, maybe let's keep them for later if we have time. But let's do an example so of how to do this numerically. So we have this data, which is linguistic data, which I saved here. So mm, wait, here. Uh, which we can look at it by taking a sample. So take a sample of 6 elements and look what do we get from it. So there are some speakers which are probably repeating these words in the Icelandic language, and there are some data about the duration of each word, and some other data which is missing for some reason, and like the position of the tongue when they're speaking, the frequencies, I guess, and other manners. And we want, for instance, to prove something that probably is true, which is if there is a statistical difference between the word durations between different speakers. So let me write it to check the duration between of words between different speakers is different. So the null hypothesis is that okay, we are discussing multiple comparisons. So we do pairwise a t-test. We do for each pair of persons, for each pair, we do a t-test. So let me simply plot the data. So ggplot data equal to Icelandic aesthetics, mapping to aesthetics. On the x variable, we put the speaker, so speaker. On the y variable, we put what we want to compare, which is the word duration. Sì, and then we do a box plot. Okay, so it is clear what I'm plotting here. These are the different speakers. And on the vertical axis, you have the duration of the word they're repeating. They're repeating many words. I would say that the I'm sure that the big line in the middle of the box is the mean of the duration of each single word. The points are the duration of the word each speaker is saying. And this box is like inside this box. I don't know if it's inside this box. Yes, yeah, I would say that inside this box there are 75% of data, more or less. I would say some a percentage of data, and some outliers are plotted. I don't know precisely the numbers, but I mean it's a graphical tool, so this box plot. And now I'm taking two guys like this BRS02 and this BTE03 and performing a t-test between the two data. Uh, but I want to do it for every pair. And R has a command that it's really makes the life really easy, which is pairwise, pairwise t-test. I put here the data Icelandic. I have to pass the data word duration. Uh, and I have to pass here the grouping variable, which is the speaker. And I would say that this will do the job. Sorry, Icelandic, of course. There is no variable called speaker. It exists only inside the Icelandic. And this performs separately many tests. Okay. Sorry. And I want to adjust the p-value. So here I'm not doing a test with a significance level of 0. So um I have to add here p adjustment. Uh, P adjust method equal to none. And here I'm really doing many t-tests because otherwise it used some correction of the p-values. So you see, many speakers differ. For instance, this guy B, this guy BT differs from everybody else, and these guys don't statistically differ, but we are performing many of them. So what do you think it will happen if we put here the Bofferoni correction? So will this table, I mean, will this value, these are the p-values of the test. Will this p-value decrease, increase? What will they do?
Probably it will increase since we're dividing alpha by n.
Yes, exactly. That's correct. It should increase. Uh, yes, and uh, they're still low, but this one, for instance, now is one. Before was 0 point something. This one has increased. It's not such a big difference now, but uh, uh, it is. I mean, it is they increased. So that was a correct answer, and uh, so this is a natural. There are other corrections also. Holmes, which is the default one, which is less conservative, so they will increase less. So in this case, now they will Holm, sorry. Now they will decrease because but they will still be bigger than the first case in which no correction have been had been made. So and there are many corrections you can do. The Bonferroni one is I mean, it's maybe an overreaction to that problem, but it makes its job. So Bonferroni is quite conservative. It's very conservative. P-values increase a lot, and the default selection is Colm. So now that this is what we did last time, and now we want to do another test, which is the ANOVA, the analysis of variances, in which we regard the corrections in this, all together. So the null hypothesis will be this one. Will be that the mean duration of each single speaker is the same. The alternative will be that there exists a pair which at least there exists at least a pair whose mean durations, mean word duration differ. So, and this is the analysis of variance. Let's simply, since we did like a chunk of code here, let's first apply the function, and then I will do how it works. I will say how it works. So there are many built-in functions for this analysis of variances. The most basic one is this analysis of variances. There is also ANOVA, I guess. Maybe this is more basic, but I will use this analysis of variances. And we put here the variable we want to predict, which is the mean duration of words. And the predictor is the speaker, and the data is Icelandic. And this gives us so word duration is not word duration. So this gives us a formula is a test, so it has its statistic, which is the this. So let me add something here. So mm, um, I want to add an option which makes the standard deviation Mm, maybe it was like pulled. Okay, I simply disregard the correction it makes naturally, which you shouldn't do. You should always take this pooled standard deviation equal to true. Well, it depends, but well, it doesn't change the output. So, okay, no, I now remember. Sorry. Uh, okay, it is better to save to save this the result of this test into a variable, and so this is a variable of class which will have a class. For instance, it is has the class of analysis of variance and linear model, and it is better to plot it using summary, has a better output, which and now I can. Okay, so the f value is the statistic of the test, and here it is a number. You still don't know what value, what does it mean, this value, but the p-value associated to this value is small. So the analysis of variance, in this case, tells you that the alternative, you should take the alternative hypothesis. So that there is the speaker, the duration of the speaker saying a word differ from, there is a list, they're not all the same means. Uh, so this is the idea. But you see, from this test, you don't know precisely uh, which speaker differ one from another. But the output is that there exists a pair whose mean that uh, that very likely mean duration of words is uh, is different. But it doesn't tell you which one in particular. The advantage is that its computation is much better, is much better, and it it is a test. It's not many tests, so it can like discover some significance difference which Bonferroni which the pairwise t-test which with Bonferroni disregards. Okay, so this is the analysis of variances, and now let me briefly say what this F statistic is. uh, is the ratio. So let me so the statistic is the ratio between the in-group variance and the variance between groups. What does it mean? Let's go back to this box plot. So each one of these groups has a variance. So if all the means were the same, but also the mean of each group have a variance, if you simply consider the mean, we see that they differ. They will have, I mean, they differ from group to group. So if the difference between the means is bigger than the difference between the variances in each group, then this is better, a better uh, hint, a better argument in favor of the alternative hypothesis. So I don't know if, so let me write it. If the variance of each single group is smaller with respect to the variance of the means of each thing of the groups, each group. Then the the argument in favor of H1 is greater, is stronger. So do you see why? I mean, if the box, if now I simply increase these boxes, then I would say that the argument in favor of each one reduces. I mean, its power. So if I stretch each single box, this this will be weaker hint. Instead, if I increase the variance between the boxes, so if I display the boxes far from each other, then it is a stronger argument in favor of H1. So the F statistics is the variance is something like I don't want to say precisely what it is, but is the variance between the means of the groups and the variance of and the in-group variance. Is the ratio. Sorry. is the ratio between the variance is the ratio. So, what do you think? The self-statistic, I mean, when it is bigger, which values of f will be, I mean, when h1 is true, you expect f to be small, big, close to a number, I don't know. Uh, so assume that I give you a number of f, f has to be positive. If I give you f equal to 20, what would you say? It is likely that h1 is, I mean, the test will give you uh, that you can react h0, or well, if f is big, it means that the variance between the means is bigger, or that this ratio, it means that this ratio is bigger. For instance, it could be that the variance between the means is big. So it means the bigger the f, the bigger either the distances between these boxes, so the vertical distances between the boxes, or that these boxes reduce. So the bigger the f is, the stronger the hint. So f equal to 20 will be a big, it is a big number. So let's check it. I mean, we already did this test. Here is 140, which is a lot. And in fact, the p-value is smaller than 2 to the power 10, 2 times 10 to the power minus 16. So it's insanely small, this p-value. So this is very big for f, for an f statistic. So uh, so do you have questions concerning uh, this analysis of variances? I don't know. I mean, I didn't explain it carefully, but it's. I mean, hope that it is clear. Um, so I wanted to discuss, if it is clear, I wanted to discuss some more, to finish the discussion about test with the last thing that I didn't mention, which are confidence intervals, because, for instance, we perform a t-test. Let's say we want to check whether I don't know, I take a vector. Yes, no, I had saved some linguistic example here from the book of Bayern. And I saved, so let's see the data of this. So this Bayern has written a book which is about data analysis for linguistic research. I don't know if this is the name of the book, but the concept is this one. And he wrote a package in R with which a lot of good examples. And let's take the data. The package is languager, so library. I have already downloaded it, of course. And we can look at some data that are inside here. So the package is check. Okay, and I can. There are some data and I chose this one for the example, which was duration of something uh, prefix. So it was like prefix duration. Well, I can go upstairs and retrieve what I wrote. So durations J. So let me simply, moreover, each data has in this package has its own explanation. So let me the durational measurements on the Dutch prefix J or G, I don't know. And I wanted to see if the sex like influences the word duration. So duration. So I wanted to take a t-test which I want to predict the duration of the prefix using the sex with on the data. It's called prefix again. No durations. Okay, and the result is negative because the p-value is great is a big number. So the difference is that is not so big. And I want to make clear what this, not clear, I mean, I want to say what this sentence means. So this sentence is that a 95% confidence interval. And so this sentence means basically that the probability that we regard this probability that if we believe in that the test, if we believe that the hypothesis uh, that allow us to use the t-test are satisfied, Then we also believe have that the probability of that mu1 minus mu2, so the mean of the durations of the prefix of males minus the one of females is in this interval minus 0.00995 and 0.008159 is equal to 0.95. Um, so there is, of course, when we do a test, there is all. I mean, if we perform an experiment, there is always the randomness in the choice. For instance, we could have chosen speakers which were by chance identical, and the actual. So we can never be sure that the means are the same, but we believe that they are in this interval, which is very small, with high probability. So it means exactly what it the how it is named this interval. So recall the interpretation of the probability as the likelihood of something to happen. The degree of belief you believe in, if you believe in the hypothesis that the test is the I mean, it is reasonable to apply this test, then this test also, as a consequence, you also believe that uh, this that the real difference between the means is in this interval with this confidence, and it is the but confidence intervals are more general, so you can make an interval for every unknown quantity. So if you have an unknown quantity, you can say, for instance, x unknown, AB is a 95% confidence interval if the probability of x in AB is equal to 0.95 or small or greater. So you find these intervals when you look at the weather forecast. So in forecast, you always find weather forecasts. This kind of intervals. And by the way, there is a book which is like which is called the Black Swan, in which some papers uh, some papers are cited where they ask participants to make to create confidence intervals. So how many to make 95% confidence intervals. Um, how many of them, of the participants, should, what percentage of the participants should, I don't know, guess wrongly the, the confidence interval, the interval, if they do it correctly. So do you have an idea? I don't know, you ask people randomly to create a confidence interval. You look at 100 of them. Each one is sure at 95% that he is right, that interval he chose uh, is a good interval. So do you have, I mean, uh, so, okay. So in the way I wrote it, it makes no, it's very tricky. So if they, so how many of the participants should guess wrongly the interval? Uh, if the 95% of, if each one has really a 95% of probability of having guessed it correctly. So it should be 95% of them should guess correctly because you allow for a 5% of errors, for a 5% of probability of making an error while estimating this interval. It is the same thing as doing a test. It's only another way to say it. But the results were that like more than around 50% of participants guessed wrongly the interval. So this means that they were overconfident. So usually this is what happens. This was just a note for these uh, confidence intervals. So do you have questions? So let me finish with these confidence intervals first with a link in which uh, uh, with some you can visualize these confidence intervals for a artificially generated data, of course, so in an easy context. But before, let me recall how. Let me say how a confidence interval, the confidence interval is generated, is computed in the Z test. So recall that we have a sample of n elements. We consider the t statistic, which is equal to the fraction, the trash between the square root of n times the mean minus an hypothesis, hypothesized mean divided by the standard deviation of x. Then the z test works in the following way. We consider that this t, we consider that t is a normal, a standard normal distribution. So it's normally distributed. So taking a frequentist approach, if we were able to generate many t's, we would see something like this one. If we perform this simulation many times, we take this is 0, t is near, so this is the on the horizontal axis we have t, and we see something like very concentrated in the center with sometimes a t which is spurious, which is really unexpected. And if we plot the histogram, we would see something like a bell shape. And it is known that 95, this is like the exponential of minus t squared divided by 2 divided by 2p. And if we take this interval minus 1.96 and 1.96, here we find 95% of the area, of the total area. So the t will be in the test tells you simply that the probability that t is in minus 1.96 and 1.96 is equal to 0.95. But t was the square root of n divided x bar minus mu divided by the standard deviation of x. So we can, this becomes that the probability that square root of n times x bar minus mu divided by the standard deviation of x is in minus 1.96. 1.96 is equal to 0.95%. And at the end of the day, the probability that x bar is in mu minus 1.96 times the standard deviation, which we can take sigma, which is the standard deviation of x, we can approximate it with the standard deviation of the sample. So, sorry, no, nothing. No, it was true what I said. So here we take the standard deviation of x bar divided by square root of n, and mu plus 1.96 times the standard deviation of x divided by square root of n. This is equal to 0.95, and the probability. So this is equal. So here the unknown quantity, we know x bar. The unknown quantity now is mu. So we want to see where mu is. So this is the unknown quantity. So fortunately, this as event is equal to the event that mu is in x bar minus 1.96 divided square root of n times the standard deviation of x bar, and x bar plus 1.96 divided by square root of n times the standard deviation of x bar. So this event, you can do your own consideration, is equal to this event, and writing the same thing. And this probability is 0.95 if the approximation is true and everything else. But in this way, we find a confidence interval. So these under the same assumptions of the Z test. Uh, um, so maybe it is better to see this problem from a practical point of view. You have your X bar, you want to find the real mu. Well, your real mu, you know that X bar will be in an interval between near mu. It is the same thing of mu being in this interval. It is the same thing that X bar is in the interval mu minus delta, mu plus delta. It is equal to the event that mu is in the interval x bar minus delta, x bar plus delta. So here it is x bar which is random, here it is the interval which is random. But the unknown is mu, the thing you want to estimate. So this is how this is how intervals Uh, sorry, this is how the confidence interval for mu in the Z test. So do I need to repeat something? Uh, I can give you this link in the chat. You can visualize. Okay, yes. These confidence intervals. Um, so here it is doing what I would do. So he generates uh, some 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 samples and computes the sample mean. He knows the real mean, which is zero in this case, and checks how many times the confidence interval built around x bar, the sample mean, contains the real mean. So let's increase the speed. He builds a 95% confidence interval. So uh, how many times do you think he will? So let's pause it. So he made like 400 like 504 simulations. How many times do you think he missed it? He missed the confidence interval didn't contain the real mean. So he builds an interval in which he's sure he's 95% sure that the real mean will be there. You do it many times independently. This is frequentist probability. So like 95% of the cases, you will see the mean there. Here is all rigorous because it is, you know, the distribution of this data, but in real life, you don't know the distribution of the data. But in this case, you can see here in this graph that he is around, if you do 22 divided by 504, you should see somewhere or less 0.95. Let me check it. So 22 divided by 4082 plus 22. This is 0.43. So more or less 0.95. And if we go on with the cases, it will be more precise. So let's do. Okay, it seems he's overestimating it. I don't know why. But more or less is 95 the confidence interval, and we can also decrease the statistic, the confidence. So if we reduce the interval, we decrease also the confidence. So, for instance, mm, I don't know, uh, if you another question would be this one. If you decrease the confidence, will your interval be bigger or smaller? No, do you have any ideas about? So if you tell me, okay, tomorrow the temperature will be around, it will be between 9 and 11 degrees, I will have a certain confidence. But if you ask me to do it with a confidence of 99%, I would say like between -1 and 23. So it's I will increase my interval. So the smaller the confidence, the bigger the interval must be, because if you take a bigger interval, more chances are there. There are more chances that you guess correct, simply because of that. So, okay. So they've seen. Okay, uh, I've seen it now. The your reply. Sorry. So if you increase, what was the question? Decrease the confidence. Yes, exactly, exactly. Uh, Thank you. Uh, so let's do a 10 minutes break. Uh, so we'll start now another completely different, well, not completely different topic, but another topic, which is about regressions, and we will start now by introducing the correlation and the correlation coefficient, and next time we'll do the simple linear regression. So let me share the screen. Uh, and we start, yes, by look at which kind of data for which kind of data we can define a correlation coefficient. So the data we want to treat is numerical and bivariate data. What does it mean? Well, up to now we have looked only at either numerical data or categorical data, but we have seen them singularly. So we have seen, for instance, have studied the vector heights, which was something like uh, sorry, For instance, a normal, a random normal distribution, 20 person, we compute the height, we measured the height of 20 people. The mean, let's say, is 170 and standard deviation 1.5. So this is a numerical variable, and we computed many statistics like the mean and the standard deviation. Now we are interested in data in data which consists in two numbers. It could be, for instance, the height and the weight of people, or like the income and the height, for instance. And we want to define a statistic that takes into account the two numbers, the two numerical data. For instance, let's do an example. So we have the variable x. So we have a variable x which, for instance, we measure. We have, for instance, 20 people in the sample. So k is equal to 20. And we measure two numerical variables for each person. Two numerical variables. X, we take some artificial data, for instance, random normal of 20 random normals of variance of mean 100, 100 and variance 4, and standard deviation 4. So, and y is equal to 1 divided by x divided by 5 plus an error, which is a normal of mean 0 and variance 1. Variance 1. And we plot these two data. So first we bind them together. So my data is a data frame. And we plot the points. Okay, so we have this graph. Now we can compute the one-dimensional, we have both x and y. We can compute actually the usual things we have already defined. So we can compute the mean of x. So let's call mu1 equal to the mean of x. So the mean of my data x. Mu2 is equal to the mean of my data y of the second component. We have also the standard deviation. So sigma 1 equal to the standard deviation of my data x, and sigma 2 equal to the mean of my data y. Sorry, the standard deviation. Okay, uh, these quantities do not speak to each other. The mean of the column x does not depend on the column y, of course. So we can like disorder doesn't so it doesn't really care if we I don't know if instead of y we if as long as the same x coordinates are at the same place, we can change the y coordinates in whatever manner we want. So we want to define a kind of different statistic. So let me plot the mean of each uh, I add a vertical line where the mean of the x component of this point is, and then I add an horizontal line in the mean of the y component. So and let me color it in red. So in the vertical line is the mean of the x component of this point, and the horizontal line is the mean of the y component of this point. Um, so I want to define a statistic. This is my aim. So what I want to define is the covariance of these points, of those 20 points. So going back to the past course we made, we actually defined what is a covariance between two random variables. Um, so let me before defining the covariance of this set of points, let me recall what was the covariance of two distributions. So of two random variables. So recall that well, if we have two random variables, x and y, its distribution function, its joint distribution function is the function which we call the pxy, which associates to each rectangle, let's say a rectangle A1, B1 times A2, B2, the probability this quantity here which is defined as the probability that the vector, the point, the random point xy or vector is in AB times, sorry, A1, B1 in the Cartesian product in the rectangle A1, B1 times A2, B2. So if we know the distribution, we know the probabilities of this random point where this random point will appear. We know the probability of this event. So in other terms, graphically, uh, let's take A1 equal to 1, B1 equal to 2, A2 equal to 0, and B2 equal to 1. And let's uh, let's look at this rectangle. So uh, so the x leave uh, have to remember the syntaxis uh, ggplot. So um, so geom rectangle creates a rectangle with where x mean is in whose edge, whose angles are x mean, y mean, and x max, y max. And so the probability distribution means we know, for instance, the probability that this vector xy falls into this blue region. So this is as simple as that. Well, it is not in mathematics. Usually, they give you the distribution function, and you want to compute everything else. Particularly, we will recall now how we define the covariance. But the difficult stuff is that of statistics is that we don't know the distribution of the data. So that's the point. But let me finish recalling what was the definition of covariance. So for discrete random variables, say x can be equal to x1, x and 1, and y it can be equal to y1, y and 2. The covariance is defined by this formula. It's equal to the sum of I, j, and go from 1 to n1 and n2 of what? Well, of xi minus mu1 times x2 minus mu2 times the probability that x1 x is equal to xi, sorry, not x2 minus mu2, yj minus mu2. This is the covariance where mu1, for instance, is the mean, is equal to the sum from I that goes to 1 to n1 of xi times the probability that x is equal to xi, and mu2 is the same thing but done with the y variable. So this was the covariance, and we will explain later what does it mean. I mean, we will visualize it in a better way when we will define it for a set of points. For general random variables, the covariance is defined by approximation of the random variables via discrete random variables. This is a procedure which leads to the definition of the Lebesgue integration, which is, I mean, it is not it's really easy, and the idea is even, well, it's not so so different from the Riemann integral, which is the one you did in high school, but is, I mean, it's not mathematics. This course, so is not. I won't explain it. And just to for a general knowledge, in particular, this approximation procedure for continuous random variables, this random variables, where there exists a function f, a density function f that goes from R2 to R, such that where plus, sorry, positive integers, such that the probability that x and y are in a rectangle is equal to the integral of this function of f x y, the x, the y. So when this happens, the distribution of x and y is said to be continuous. In particular, this infinitesimally, it is written in this way also. Maybe you have seen it, but you don't need to know this. Just for general knowledge, the probability that x and y is in the x, the y is equal to f xy times the x, the y. This is the infinitesimal version of the above. Okay. You don't need to know. In this case, the covariance between x and y is equal to the integral uh, of the function x minus mu1 times y minus mu2 times fx y dx dy, where mu1 is the mean, is equal to the integral of x times xy dx dy, and mu2 is also the mean, but of y. So this is the theoretical covariance. That we can compute once we have the distribution of two variables. We will never compute this because we'll never have a distribution. So I could have skipped this part, but it is nice to know that there is a theoretical, an ideal covariance behind the data. So otherwise, when you compute the covariance and you have many data, you may wonder why this covariance, to what thing this covariance resembles, where there is a theoretical covariance behind that is it's an ideal actually, but in the reality you observe the data. So let me define what is the covariance of a set of data, which is I could have skipped this part. It was a reminder. Okay, so uh, of data. So assume let x and xy be the following collection of data. So x and y be a collection of points uh, x1, y1, xn, yn. Now the fact that they go paired, that x1 goes paired with y1, it's important because they could be like the height and the weight of a person. So this is important, and um, we can define the covariance between this set of points in the following way, as the mean of the difference between of, of x1 minus over line x, its mean, times y1 minus its mean, and we do this for every point in the sample. So we have to compute also xn minus the mean of x and yn times yn minus the mean of the mean of y. Well, I recall that the mean is simply the usual one, which is the is x1 plus plus z. And the same thing goes for y, the mean of y. Of the, Okay. So this is the definition. Probably R computes divides, instead of dividing the covariance by n, it divides the covariance by n minus 1. So probably but the difference is, when, especially when n is big, really negligible. Um, and let's see what does it mean, this formula. So um, let's do the same plot as we did before. So was this plot here. Um, so on the vertical line, there is the mean of x, so x bar. A point on the right, which are the points for which x1, xi minus its mean is positive, are the points on the right of this vertical line. So now uh, I color the points, the sector of the plane uh, where points uh, falling there have a positive xi minus over line x. So in order to do this, we add an annotation. And annotate x xe the mu1 and in while in the syntax is the following. I want to put a rectangle, so annotate rect rectangle, and I have to put the x mean. It will be the left bound of this region, which will be mu1, and x max will be equal to infinity. Then there are y mean, which is equal to minus infinity, and y max will be equal to plus infinity. And then I fill with a color this region, which I take the color which I created here, which I used here, which is this one. So in this region, the product xi of the y of the x component of the points minus its mean is positive. So in this on this region a point xy uh, satisfies that xi minus overline x, which is mu1, is positive. Um, on the region say this one, where now I do the region for which y I minus y is positive. So on this region, yi minus y bar is positive. The question is, when is this? When is the product y I minus y bar and xi minus y minus overline x positive? Well, when each one of the when they are are both positive, either positive or negative, when they have the same sign. So otherwise the product is negative. So coming back to the graph, in uh, the fact is that let me go back and take this graph here. Uh, on the blue parts, the product xi minus if a point xi yi is such that the product xi minus the mean times yi minus the mean of the y component is positive whenever is in the blue region, negative otherwise. So in this case, there are much more points in the blue region than in the red region. Of course, this product will be bigger for points which are very far, far from these red lines. But by simply by counting them, and also because the points in the blue sectors are very far, so this covariance should be, we expect it to be positive. And let's check it. Is positive. So we could have also computed it by doing the mean of x minus the mean of x. So in my data, x. Um, minus the mean minus y minus my data y minus the mean my data y. This should give me sorry, my data. This should give me the same result, but R probably divides by uh, non-function mean. So, okay. Oops. So it is almost the same, but really here it doesn't take the mean R for computing the covariance, but takes the mean divides by n minus 1. So we should multiply by 20 and divide by 19 to obtain the same result, because 20 is the size of this vector x. I may have to put a proxy, of course. So yes, is this thing, and okay, this the covariance. We have checked that it is positive here, and when the cloud of points is something, the points don't do strange stuff, it really tells you the covariance, how these points are, well, no, the covariance no, is the correlation coefficient that tells you this. So let me explain it. So Yes, but before doing that, let's recall an important, very important theorem that independence and covariance. Recall a theorem that covariant, independent variables imply uncorrelated variables. The converse is not true, as we will show. What does it mean, independent variables? Well, let's plot some independent variables. Let's take x as a random normal of, let's say, 100 instances of a normal, no, let's say 50, distributed around 0 with standard deviation 2, let's say, while y will be a random exponential. Since I've built it, I know that they are independent, and let me plot it. Let me save it to my data. I plot this data, and okay, this is the plot of independent data. What does it mean? Well, it means that however I fix, let me fix two regions, like between -3 and -2, that x lives into -3 and -2. So if I know that x is here, I look at the y-axis, I see the same distribution that if I take x equal to I don't know, 2 and 3, and I see the same distribution of points, or x in between 3 and 4, where if x is in between 3 and 4, I don't see any point. So I don't know. I can, but if I were to see another point there, the height would be distributed independently of x. So the heights of these points do not depend on the x point, on where the x is. So let me take two strips. So x Smith, a strip that starts at -3 and arrives and ends at -2.5, and it is unbounded on the y-axis. So x, y mean is equal to -inf, and y max is equal to inf. And I fill it with a color. Let's say, sorry, I fill it with the color that I used before, which was this, this color here. Uh, what happened? I simply One, two, three. While it does, it did like that. Explode like that. Jump point. I didn't put clearly. Of course. Uh, okay. If I look at this strip, and if I look at another strip of a different color, I should see the same distribution in the heights of the points. And this for each strip that I want to plot. For instance, from 1 to 1.5, let's say. Um, let's take some more points, 70. Um, and change the color of the second strip. So the distribution of the y component in this strip, they are the same. Now the points are quite few, so there are only two fall in the first strip, so we cannot really compare the distribution of the heights. But if we were to add points, we would see the same density of points. So we can try it. I don't know if it will be readable or not, but let's add 200. Let's go to 200 points and see what happens. So more or less, it's clear that now because on the red strips there are more points, but because it's more concentrated, but the distribution of the heights is more or less the same. Let's go more points, like 1,000. So you see, it's really difficult to distinguish if you will only look at the points falling into the strips. And I can do this for each strip. The points are independent, so the strip where the strips are placed really doesn't matter about the distribution of the heights. This is the meaning of independence if you want to see it graphically. Um, Now, what happens if we put some data which is correlated? So if we put some data which is correlated, really well, it's we expect to see different y component into each strip. So let me just simply do the same plot with other kind of data. So with correlated data. So let me take copy and paste it. But now we take correlated data by taking y equal to x plus this exponential. So now the data will be different. Okay, these are really correlated. And you see the heights of the points falling in the blue strip. We expect to see them we expect to be them lower, to have smaller heights, while on the red strip the heights are bigger. So these are not independent. The following data is not the following. the following data is correlated and dependent. It is correlated because you see the correlation measures for this kind of data how much they are inclined, the slope more or less for this kind of data. And they are dependent because if we look at the two strips, we see different distribution of the heights, while this here not. So this gives you like sometimes somewhat a reason why data which is correlated, which has a covariance which is not zero. So let me write it. Correlated means that the covariance is not zero. And this is always true. Well, if the covariance is not the ideal covariance is not zero, then the data is not independent, while the converse is not true. Why? Because data could be depending in really strange manners. So let's look at this plot. Let me copy image. Fast. You see, if the data is like here in the first row, well, we expect the covariance more or less tells us also so zero covariance here is the independent also coincides with the independent case, and these other cases where the covariance is not zero correspond to dependent cases. But here, the covariance is, in the last row, the covariance is always zero, but they are not at all independent, because if we change these two strips, we see different distributions of the heights. So the y component really depends on the x. So, but the covariance is zero. Why? Because you see here, there are the same amount of points on each direction. How, I mean, you can compute it, you plugging, I mean, somebody computed it and the covariance is zero. But they are not at all independent. So the above picture, the third row of the above picture shows that a small covariance does not imply independence. Uh, should be this is an important point. It's simple, but it has the point to be remarked, because the covariance is simply a number. Many data can give you the same covariance, and also, for example, covariance zero is given by these crazy figures here, which are not completely out of one's mind. So this was a remark. In conclusion, covariance, if you assume independence, So independence implies covariance should be zero, is zero. But this is the ideal covariance, the covariance of the samples. Should be zero. So that this is another topic that we will discuss now. While covariance, while the converse is not true. Um, okay, now we finish with what actually with the correlation coefficient. So the problem is difficult to make. The problem is the following: that it is very difficult of covariance is the following: that if you take the covariance of a sample x, y, and you multiply a sample by 10, this is equal to the covariance of x and 10, and you multiply the second sample by y, and it is equal to the covariance of x and y multiplied by 10. This means that is a number that relies on the units of measure, and it is difficult to make general claims, statistical claims on such kind of data. In some sense, we should have some normalization since conclusions cannot be depending on the measure. So if I measure I don't know, the height of people in meters, I get one result, and centimeters another result. So we want to normalize it. So we define the Pearson's correlation coefficient in the following way. We therefore define the Pearson's correlation coefficient by this following formula, which is the Pearson's correlation coefficient between x and y is equal to the covariance between x and y divided by a normalization, which is the standard deviation of x times the standard deviation of y. As simple as that. In this way, this tau doesn't have units of measure, and all the tests are doing using this correlation coefficient. Of course, we can compute it. Let's take correlation between x and y. So let me, before doing that, let me plot it, ggplot. So these are very dependent, this data. We go and look at the correlation coefficient, which is 0.89. So this core computes the Pearson's correlation coefficient, which is this quantity here. What properties does it have? Does tau have? Well, the most important one is that tau is equal to is a number between -1 and 1. This is the most important thing. Tau equal to 1 means that they are tau equal to 1 means that the data is on a line. While tau equal to 0, for tau equal to 0, the data is said to be uncorrelated. And if you go back to this picture, here, what is pictured here is the tau is the Pearson's correlation coefficient, these numbers here. Okay. Then this is the Pearson correlation coefficient. Yes, what else can be said about this coefficient? Well, of course, it has, if one thinks in pure mathematical terms, we have this tau defined also at the level of distributions. What do? We get our data, and we define this tau empirically, this Pearson's correlation coefficient, and uh, we want to see whether the data, we would like to test whether the data is uncorrelated or not. So the problem is the data that I observe uncorrelated. If I knew the distributions, I could answer this question by computing the ideal tau, the one using the real covariance of the data, which we don't know, but we don't know it. We have some data, compute using that data tau, but since now this tau is based on the sample, on a sample, even if the data is uncorrelated, tau could be positive. Is tau is different from zero. Since it is a random number, it is almost impossible to have it precisely equal to zero. We have a test that checks whether or not tau is significantly different from zero. So that is that to check whether or not the difference of tau from zero is due to randomness or to a real difference or to a real correlation. Of course, there is, and we have this test on R, which is like called test. We can put X and Y and look, see that in this case, the p-value will be really small. So you see, the p-value is really small. And actually, to perform this test, we are really computing the t statistic with 98 degrees of freedom. So we are not doing more advanced mathematics than the one we did before. So we already did the mathematical part. Now we are doing the more statistical part. So this is the test to check that checks whether or not this Pearson's coefficient is significantly different from zero. And here the alternative hypothesis is true. And in fact, the p-value is really, really small. The alternative hypothesis that the true correlation is not equal to zero. And the true correlation is this correlation you computed using the distributions that we don't know. It's like an ideal. So in the next lecture, we will introduce other two kinds of correlations, and we will start with the linear regression, which is the an easy and the linear regression is not so difficult, but the application of it is tricky and it's really used, so it's important to know it. Okay.